Welcome to the course on Foundations of Computational Materials Modeling. So I hope you would have seen the introductory part of the lecture where I gave you a very brief overview as to what we might be doing. So in order to explain some of the details as to what are all the various things that you might actually need in the course, we will go through them. We will go through some of the introductory material once again. So I would require that the students who are registering for this course actually have a basic material science background at the level of BE or B.Tech. They should also have some background on basic programming using MATLAB. There will be several MATLAB programs that we will be writing in the first part of the course, and which is the basic purposes of this MATLAB programs is to actually create input files, or is to create codes so that we can generate various kinds of crystal structures. So I would expect that you have a reasonable experience in programming with MATLAB. If you don't have, I am sure that there are several online. If you don't have, I am sure that you have several online versions, online tutorials from where you can learn this MATLAB programming, and also probably NPTEL lectures. We will be working with LAMMPS in the third part of this course, where we will be teaching you to write very simple input files in order to run some molecular dynamics simulations on gases, on metals, and also on ceramics. For that, you will actually need the LAMMPS code to be on your laptop or desktop. So please make sure that you already have an installed and a working version of this particular software on your computer. And in order to visualize the results of that is generated by LAMMPS code, you will need something called Ovito, which is also freely available. You can simply download and install it on your computer. Please keep it ready. We will not be needing both LAMMPS and Ovito in the first 2/3 of the course, but it is a good idea to have them on your laptops and figure out any issues that you have in installing them, so that you would not have any trouble later on in the course. The evaluation pattern will essentially consist of you doing about 12 assignments. This is a 12-week course, so we have planned about one assignment per week. Most of these assignments are expected to be answerable by looking at the slides, and some of which you may have to think a little bit, like I mentioned in the introductory course, a mid-semester examination, and then a final examination. So with that brief introduction, I would like to start talking about computational materials modeling in a very broad sense. As the name implies, computational materials modeling involves using the computer to basically understand the different properties of materials. In particular, it's possible for us to look at mechanical properties, chemical reactions, why certain chemical reactions occur and why they don't. Electronic properties are also possible. Optical properties and magnetic properties can also be evaluated using computational tools. Not only is it useful in understanding physics or the reasons behind certain observed properties in the materials, it's also useful for predicting new materials and new phenomena which might actually be happening inside the material. So when you perform an experiment, and if you are not usually able to explain why you observe a certain thing, then it's possible that you can conduct some simple molecular simulations in order to try to explain that phenomena, or to find reasons as to what atomistic level phenomena is actually causing your observed experimental plots, for example. Okay. In atomistic modeling of materials, it's also possible for us to explore phenomena at various lengths and time scales, especially lengths and time scales that are not amenable to experimental observation easily. So by that I mean that if you want to look at how dislocations are moving in a material, or you want to look at the kind of point defects that are going to be generated when a material is being bombarded by ions or neutrons, then such things become hard to observe experimentally. Under such conditions, it's possible for us to look at how simulate these processes on the computer, and this helps us gain a deeper understanding, at least qualitatively if not quantitatively, on what could be actually happening in these materials. So of course, that's with respect to both the lengths and time scales. You could be looking at very extremely small length scales that you can really not capture using experiments, and molecular dynamic simulations or many atomistic methods are working with systems at the atomistic level, and therefore you would be able to get atomistic level details from these calculations. So that is the basic purpose of this course. In addition to that, there are time scales issues also associated with physical phenomena. For example, if you talk about radiation damage in general, you are going to be creating point defects. So when a neutron comes and hits a material, it is going to generate point defects in the material, and this entire process usually happens in the order of, say, 10 to 15 picoseconds, and it is usually hard to see this using experiment, if not impossible. So molecular simulations helps you understand these processes even though they are occurring at extremely small length scales and time scales, because the method itself is adapted to actually work in these time scales. So you will see more as to what this essentially means when we talk about molecular simulations. So that being said, it doesn't necessarily mean that experiments are not important. They are extremely important. The discrepancy that you observe in a computational result and with that of the experiment must properly be analyzed, and you must be able to give some sort of a reason as to why your simulations are not matching with the experiments. There could be several reasons for it, but you should make sure that the reasons are as logical as possible so that your simulation results are at least qualitatively acceptable. But it is usually, that being said, I should also mention that it is very hard to expect quantitatively same numbers for many different problems between the computational result and the physical result. For example, when you are trying to calculate the elastic properties of copper, then you generally perform the experimental results with a dog bone specimen, which is going to consist of a large number of polycrystalline grains. However, when you are trying to do that, when you try to match these results with the simulations that's performed on a single crystal copper, and you don't expect the same kind of values in the both, you should be able to logically conclude that one thing is going to consist of large number of grains, where the other is going to consist of a single crystal. A single crystal is probably a little bit more stronger than the polycrystal, and the specimen that you are using in your laboratory probably has a large number of defects, and these are not the kind of defects that you have simulated explicitly on the computer. So you need to be able to draw some logical conclusions based on which you will be able to say that the computational value that I got for my Young's modulus or the yield strength is actually not too bad. Okay. More than quantitative comparisons, we generally use these computational results for qualitative purposes to understand new phenomena and to explain something that we are not able to immediately see from experiments. So I would like to now talk about what are the various aspects that are covered in this course. This course is basically divided into three parts. The first part is called as Fundamentals of Crystallography, and the main objective of this part is to help you interpret a crystal's space group. So we are given a crystal structure and we are told that it belongs to a certain space group. We will talk about what space group means when we are actually talking about it, but the first part of the course is essentially meant to help you generate these crystal structures on the computer, which is basically the first step in starting to conduct some computational simulation on crystals. So at the end of the first part, given the crystal, the lattice constants of the crystal, like for example the A or the angles that is existing between the various lattice vectors and the corresponding space group, along with information on what is referred to as the Wyckoff positions, which refers to the various positions of the atoms inside the crystal structure. We will be teaching you how to write a small MATLAB script in order to generate these crystal structures and visualize them. These are obviously not standalone. They will actually be useful in the third part of the course, where we will actually use the LAMMPS simulation software in order to perform simulations on these crystal structures. So once you understand the first part, a small portion of the last part is actually you can actually start doing that. You will be able to generate these crystal structures and in LAMMPS and prepare them for actually further analysis. Then in the second part of the course, we will be dealing with statistical mechanics. This is going to be a little bit of a theoretical portion of the course, where we basically provide a very brief overview of statistical mechanics, just to emphasize its purpose and its connection to molecular dynamics simulations. Statistical mechanics is a very deep subject on its own, and one can take several courses in order to understand this deeply, but the purpose of having statistical mechanics here is only to see how we can connect some theoretical formulation to some computational technique, basically the theory of statistical mechanics to the computational technique of molecular dynamics, and why, and trying to convince you why molecular dynamic simulations actually work. So that is the reason why we have this brief overview of statistical mechanics. And then finally, we will have a basic introduction to molecular dynamics, followed by introduction to LAMMPS, where we will teach you how to write certain simple input files. So before writing the input files, we will teach you some basic commands that LAMMPS already has, and you should be able to generate these input scripts for very simple systems, and the same idea goes on to developing input scripts for complicated systems as well. So we hope that once we provide this basic background, you will be able to take it further and do more complicated things with it. So LAMMPS is actually a molecular dynamics simulation software, if you are not familiar with it. If you just Google up LAMMPS, LAMMPS, there is a 2M there, that is not a typo, you will be able to get into the website of LAMMPS and you can try to read up a little bit as to what it does. Of course, we will be giving more deeper introduction to LAMMPS when we actually reach that part of a course. Okay, so we want to be able to run some simulations, analyze some of the data, and visualize the results. But that being said, you need to also understand that this is only an introductory course. There are so many things that can be done with molecular dynamic simulation softwares. We will not have the opportunity or the time to explore the entire gamut of problems which can be dealt with using LAMMPS. So, but however, I do believe that the foundations that we provide here will help you understand things on your own by reading the documentation. So with that, I think I've covered the basic introduction that we have for this course. Now I would like to talk a little bit about the general philosophy based on which several computational modeling tools work. Specifically, the manner in which we have is the manner in which it works is there is something that I call as the engine, which is basically a C or a C++ or a Fortran or a Python program that is written to us, that is written and given to us, or we could write them, but the purpose of this course is not to write codes, is to use this code called LAMMPS. So imagine LAMMPS or any other computational software to be this engine, and you need to provide some inputs to this code, and the basic inputs are two things. One is how are the atoms arranged in the material that you are talking about. So we're talking about atomistic level computational tools. So we need to provide the positions, velocities, or molecular coordinates as inputs to these codes. And then we need to tell how these atoms or molecules are basically interacting with each other. These are the two basic inputs that you generally need to provide to this LAMMPS. And in addition to that, the engine by itself will have certain capabilities where you are able to tell what needs to be done with the input that you have provided. For example, you might want to change the temperature of the system from 10K to 300 Kelvin. How to do that? So there will be several commands that this engine offers, or this software offers, where you will be able to specify these things in an input file, and then you do something called as a running of the input file. So you run the engine with this input script that you have provided, and the engine actually provides you with some output files, and you will be actually either visualizing the data, or you will write other codes to analyze the information that is generated by this engine or the software or the code that you are basically using. Okay, but that doesn't end. You have to connect it to the underlying physics that that you are looking for, right? So this is the general idea behind almost all computational modeling. So if we are talking about molecular dynamics simulations, then you will have to give it how the atoms of the crystal structure are actually arranged. Say for example, if you're talking about copper, if you want to analyze copper, you will have to specify the positions of the copper atoms in the unit cell and tell how many times the unit cell is being repeated in the x, y and z direction, so that you have a reasonable sized simulation box that would essentially consist of the positions and not always but sometimes the velocities of all the atoms consisting your simulation box, which is there in your simulation box. But it's not just enough to give the positions. You also need to tell the system how the copper atoms are going to interact with each other. That means when the copper atoms are coming close together, how is the energy of the system increasing? If the copper atoms are going away from each other, how is the energy of the system changing? So this sort of an input is also needs to be provided for molecular dynamics simulations, and which is what is our focus in this course. For other types of simulation softwares which deal at a much lower scale, for example ab initio calculations, where you will also be dealing a little bit with, not a little bit, you will also be dealing with electronic degrees of freedom. In addition to atoms, you also need to talk a little bit about how the electrons are actually arranged around the atom or the ion in some specific manner. And you also need to give some inputs to talk about how these electrons are actually interacting with each other in various ways. So that is not the focus of this course. We will only talk about molecular dynamics simulations here. But while I said that, it's a good idea to know the differences that is existing between molecular dynamics, ab initio calculations, and something called as Monte Carlo simulations, these are the three broad categories of computational materials modeling. We will be dealing with the central one, which is molecular simulations. So let's start with the ab initio methods. Ab initio means from the beginning. Basically, you have to solve the Schrodinger's wave equation in ab initio methods in some approximate form. Okay, so the foundations that is required for you to understand as to how this method works is quantum mechanics. Okay, so density functional theory is an approach by which you can actually solve the Schrodinger's wave equation is a numerical, basically it's a numerical method or technique by which you can actually solve the Schrodinger's wave equation. Since it has a large number of degrees of freedom, including both atomic and electronic degrees of freedom, you can probably deal with at most hundreds of atoms in this particular technique. And generally, people deal with only the ground state, which is the 0 Kelvin or the 0 temperature state, when they are looking for various properties using these methods. And there are methods which combine a little bit of molecular dynamics simulations and ab initio methods called as ab initio molecular dynamics. And there, since there is some dynamics, since the temperature is not 0 K and there is some finite temperature, the atoms are actually oscillating about their mean positions, and it is possible for you to deal with time scales in the order of a few picoseconds. So in summary, for ab initio methods, the foundations that is required is quantum mechanics. You solve the Schrodinger wave equation, or you use an approximate method, a numerical method such as the density functional theory in order to solve the Schrodinger wave equation. Because you are dealing with atoms and electrons together, you have a large number of degrees of freedom, and consequently the total size of your system will be in the order of maybe 100 or 200 atoms. But for several properties, it is sufficient for you to have these many atoms. For example, the formation energy of an isolated vacancy, or the amount of energy that is required for an atom to make a jump from one lattice to the other. So for such properties, ab initio calculations provide extremely accurate and reliable calculations in order to get these numbers. However, like I mentioned before, if it's just ab initio calculations, generally people use the ground state of the material, which means the atoms are not at a finite temperature, they are not oscillating about their mean positions. However, methods such as ab initio MD combines a little bit of molecular dynamics and quantum mechanics, or ab initio techniques, where they allow the atoms to actually vibrate a bit. But even here, the degrees of freedom, number of atoms, or the number of atoms and electrons that need to be taken into account is a large number. You generally are not able to deal with more than a few hundred atoms with existing computational resources, and deal with temperatures beyond a few picoseconds. Molecular dynamic simulations, on the other hand, are classical. The word classical often refers to the fact that we solve Newton's laws, Newton's equations of motion, in order to track the positions and the momenta of all the atoms comprising the system. You use what is referred to as empirical potentials, which is to be viewed as some sort of a nonlinear spring that is connecting the atoms together so that the entire system stays together. So you need to connect them in some way so that they are staying together. So these are called as empirical potentials or interatomic potentials. Because we don't have electronic degrees of freedom associated with molecular dynamic simulations in general, and we are solving the classical Newton's equations, it is possible for us to deal with a huge number of atoms. For example, people have done from 1 million to 100 million atoms simulations using molecular dynamic simulations. Molecular dynamics, as the word implies dynamics, it is time dependent, which means you can capture the finite temperature behavior of the systems. So if you are going to simulate a piece of copper at 300 Kelvin, you will actually see these atoms vibrating about their mean positions at that temperature. So since the numbers of degrees of freedom is a little bit more, can be handled a little bit better than what ab initio handles, so it's about 10 power minus 11 to 10 power minus 9 seconds can usually be captured using molecular dynamic simulations. That's close to a nanosecond, which is still on the higher end. So is usually, typically, the time scales are on the order of few hundred picoseconds for molecular dynamic simulations. For Monte Carlo simulations, the foundations is still statistical mechanics. Of course, you need some statistical mechanics also to understand molecular dynamic simulations, but instead of explicitly moving these atoms by solving Newton's equations, they are based, the moves of these atoms are based on some probability, and it is possible for us to get several thermodynamic properties of the system. And because you are not explicitly integrating the equations of motion like you do in molecular dynamics, it is possible for you to have slightly a larger number of atoms and explore slightly larger time scales in Monte Carlo simulations in connection with atomistic calculations. Monte Carlo simulations can also be used for several other things. So these are the main classifications of various tools that are generally used for computational materials modeling. There are several, so let us now talk a little bit about, before going into talking about how we actually build these crystal structures, or how statistical mechanics connects the microscopic properties of matter and why to macroscopic properties, and why molecular dynamic simulations work. It's a good idea to take a look at some examples from existing research articles to see how people have used molecular dynamics simulations in their research work and what sort of information they are able to get by conducting MD molecular dynamics or MD simulations, so to speak. So molecular dynamics simulations can be applied for a wide range of, to get ideas on wide range of properties. Some of them are determination of thermomechanical properties such as the elastic properties. For example, you could get the elastic tensor, elasticity tensor of a given piece of copper or any other metal for that matter, and get the elastic constants of the material. So instead of performing an experiment, you may be actually able to conduct a simulation to get a ballpark value for these constants, which may be used in finite element simulations, for example. You can get the coefficient of thermal conductivity of a given material, provided certain conditions are satisfied. You can get how fast atoms are actually diffusing in a given metal, in a given material, and this is extremely important to understand concepts such as segregation and several other issues in material science also require these diffusion coefficients. Basically, you can actually look at indentation. So I will show you some examples in a little bit, what sort of indentation studies have been carried out in order to understand how certain ceramics behave when they are subjected to indentation. Now, nanocrystalline ceramics behave when they are subjected to indentation. Then you can also talk a little bit about or obtain information on phase behavior, what different phases of a given materials can exist, and what are the conditions under which one phase can actually transform to the other, and understand the thermodynamics of these different phases is also possible using molecular dynamics simulations. In addition to these properties, we also can study extreme conditions. One of the examples that I already gave you is looking at radiation damage behavior of materials. So radiation damage, for example, if you look at materials being placed in the nuclear reactor, they are constantly subject to radiation. So when I say radiation damage, it essentially means an ion or an atom or a neutron coming and hitting the material, say the structural material which is holding the nuclear fuel, for example, this particular material, the atoms in this particular material displace from their original positions because of this bombardment, and a large number of point defects like vacancies, interstitials are going to be generated, and over a period of time these vacancies and interstitials actually degrade the material's properties. So radiation response is one very effective example, is a good example where molecular dynamics simulations is extremely useful, because the time scales in which the point defects are actually generated and the time scales in which molecular dynamics simulations function are comparable. So these results could actually be very useful to get an insight as to what is happening at the atomistic level. Then you can also perform high strain rate experiments that are usually not possible in practical situations. You can pull the systems at various rates, for example, and to get how strain rate is actually affecting the mechanical behavior. However, one should understand that the strain rates that are generally obtained in molecular dynamics simulations could be unrealistic, and one needs to make a very careful, one needs to perform a very careful analysis to connect the results that is obtained from molecular dynamics simulations to experimental data, right? So that being said, various types of materials are currently being researched when it comes to molecular dynamics simulations. People have looked at metals, ceramics, liquids, gases, polymers, proteins, composite materials, etc. have all been studied using MD simulations. This course will generally look at some examples of ideal gases, metals, and a simple example which uses ceramic.